All right, so I would like to take a moment to talk to you about our concept of conservation of momentum. Here we will be talking about a situation where we have two objects that are going to collide with each other. And we are going to look at them as two different classifications or two different types of collision. First, we're going to discuss an elastic collision, which is where our objects are going to collide and then they're going to move independently of each other after the collision. So if we were going to illustrate this type of situation, we would have two objects. We'll just call them object A and B. And one object could be moving, both objects could be moving. At this point, it really is not important that we know the details. What I want you to understand is that each individual object has some amount of mass, and each object has some velocity. Where that velocity is a value greater than 0 or 0 is not important. So each of these needs to be identified. We typically use a 1 and a 2 to identify which is our first object and which is our second object. Here you can see I have them labeled A and B, but I'm going to refer to object A as M1 or object 1 and object B as M2 or object 2. So first we need to understand that since we're talking about momentum, let's just review that momentum is mass times velocity. This first object, object A, is going to have its own momentum. So if we knew what that object's mass and velocity were, we would simply multiply those two things together to find out how much momentum object A is bringing to our system. And so we would note that with an M1 and a V1. Object B has its own momentum, so we would take its mass and velocity and multiply those together to get object B's individual momentum so that we know how much it is bringing to the system. Now, when we talk about conservation, we say that the amount of momentum that we have is conserved, which means that it cannot be created or destroyed. It is always accounted for. If any goes missing, then it has to have simply been transferred to something else. So what we need to find is how much momentum do we have in our system before the collision happens. And so we would just take those two momentums and we would add them together, and that would tell us our total momentum available in the beginning. Then the collision takes place. That is what this arrow indicates. According to our definition, these two objects are going to continue to move independently of each other. So I would just draw them again separately, object A and object B. Now, understand that the masses do not change, so whatever the mass was of object A, that's the same mass over here, and the same would be true for object B. The velocity that they have, that will change according to how the energy is transferred. Because we're not dealing with specific numbers right now, we would simply say that if we wanted to know how much momentum we have in total, we would do the exact same thing we did before the collision. We would need to find their individual momentum. So the momentum would be the mass times velocity of the first object for object A, and it would be the mass times velocity of the second object for object B. And we would simply take those numbers and we would add them together. What we would find, should we have numbers to plug in, is that this total value and that total value would be equal to each other. And so our equation says that we set them equal. Now, it's important that you understand that the values that you plug in here have to be specific to that object prior to the collision. So technically, we should put a little I for initial with each of these, and we should put an F for final on this side to indicate that it's after the collision has taken place. Most students, however, prefer to just say MV plus MV equals MV plus MV, which is completely fine as long as you are keeping the information separate and combining those numbers according to the situation that you're given. I will typically write it as an M1, V1, M2, V2 on each side. Again, just to make sure you don't mix up your variables. And that's the idea behind elastic collisions. Inelastic collisions are going to be slightly different. In this case, we have two objects that are going to collide, But now, rather than continuing to move independently, they are going to move together. We often say that they stick together. So now, after the collision, they're going to move as if it's one new, larger object instead of two individual objects. And so here's how we would draw that. Again, we would start off with our two objects, A and B. Each one would have its own momentum, so we would take the mass of the first object times its velocity to figure out how much momentum it has initially. We would take the mass of the second object times its velocity to figure out how much momentum it has initially. And we would add those two together to determine what our total momentum is. Now, in this scenario, after they have collided, they are no longer going to be drawn as two separate objects. They are now going to be drawn as if A and B have joined together. Now, that's going to change how we write the equation on this side. We need to show that these masses have combined. So what we will do is, rather than calculating their momentum separately, let's just pretend we had numbers here. If object A had a mass of 2 kilograms and object B had a mass of 3 kilograms, then we would say that 2 plus 3 would give us a total of 5 kilograms acting on this side. Well, the way that we write our equation is that we would show that we're simply going to add those two numbers together. Whatever the mass of my first object plus the mass of my second object would represent this entire mass that is now moving. This whole thing moves together with some velocity in whichever direction is appropriate. So we would say one mass and one velocity, and that's how we would calculate our total momentum on the right side or after the collision. And so this is how we would write our formula for inelastic collisions. Now, the questions that you're going to be asked to answer in your assignments are typically going to provide you with some values, and they're simply going to ask you to find the missing value. So I know some of you would like to see an example, so let me just draw a couple of examples for you. So let's go back to our initial elastic. So here we have an object, we're going to say M1, has a mass of 1 kilogram. Let's say that this object is moving to the right with a velocity of 2 meters per second. It's going to collide with object 2, which has a mass of 2 kilograms. And let's say that this object is moving to the left with a velocity of 2 meters per second. Now, when we go to fill these into our equation, again, we have to make sure that we keep each variable isolated from the other in our calculation. So M1 V1 plus M2 V2. So we would simply plug in these numbers. The mass of the first object is 1, velocity of the first object is 2, plus the mass of the second object is 2, but before I plug in that velocity, let's just double check our drawing. It says that the object is moving to the left. So rather than having a 2 meters per second, because it's a vector, we need to make that a -2. Remember that momentums are vectors. So we would put in a -2 as our velocity in our calculation. Then we would simply multiply these values and add them together. 2 times 1 is 2, plus 2 times 2 is 4, but that would be a negative 4, which means that our total momentum before the collision is a negative 2 kilogram meters per second. Now, if this is an elastic collision, then we know that afterwards they are going to stay independent of each other. And so let's just assume that you were provided with the information that says that the first object is now going to be moving to the left with a velocity of 1, so technically that'd be a negative 1 meters per second. What is the velocity of object 2? So we would simply take our mass and velocity of the first object plus our mass and velocity of the second object and add them together, solving for the unknown variable. I would plug in my numbers. Now again, this is the same mass from the beginning, so M1 is still 1 kilogram and M2 is still 2 kilograms. So when I substitute my numbers, I would have 1 times a negative 1 plus 2, and then this is going to be my unknown. So I'm going to simplify this side as much as I can. I have a negative 1 plus 2v. Now, I cannot reduce this anymore. So what we need to understand is that these two sides are supposed to be equal. So I'm going to take the negative 2 that I found on the left side, and I'm going to set that equal to the negative 1 plus 2v that I found on the right. In order to solve for v, remember that these two things are connected because they're being multiplied, so we have to follow our order of operations. We cannot separate these first. So the first thing I want to do is get rid of that negative 1. This is basically subtracting 1 from the 2v, so we are going to add 1 to both sides. So I have a negative 1 equals 2v. Now I can separate that 2 and that v by dividing. So we get v equals a negative 1/2, or we would say that v is equal to negative 0.5 meters per second. And that's the idea behind all of these collision problems. You simply need to identify what information you have for each variable, and then you will plug them into their appropriate place, simplify your math as much as you possibly can, and then solve.